everybody. Welcome back to Markov chains. We have yet to define a Markov chain. We are in a little bit of a review mode for this video and part of the next video, but then we'll get there. In this video, we are going to apply the law of total probability to a problem. Now, we learned about that in the previous video, and we're also going to talk about Bayes' rule. Now, I know you haven't been with me that long, but you have been with me long enough to know that I hate rules because I can't remember rules. I don't have enough space in here. And if you are thinking of mathematics or probability and statistics as a bunch of rules, then you're going to have a hard time because you're going to be really thrown when something small changes. So let's try to understand what we're doing at all times if we can. The Reverend Thomas Bayes, brilliant, and he gave us so much of what we do today in modern statistics. But Bayes' rule, I don't think we needed him for this one. You and I can figure this out on our own, and so that's what we're gonna do. As a motivating example, I have 3 boxes, or if you wanna be more traditional in statistics, 3 urns. And in each box or urn, I have some number of red, green, and yellow balls. So you can see in this first urn, I have 2 green balls, 3 red balls, and 1 yellow ball. In the second urn, I have 1 green ball, 2 red balls, and 3 yellow balls. And in the third urn, I have 2 green balls, 1 red ball, and 3 yellow balls. So I've got an experiment for you. I'm gonna roll a fair 6-sided die. And if I get a 1 on the die, we're gonna choose box 1. If we get a 2 or a 3, we're going to choose box 2. And any other outcome on the die, we're going to choose box 3. And then we're going to go into the box that we chose and randomly select a ball and observe it. So I have a question for you. What is the probability that at the end of this experiment, we are looking at or holding a green ball? Let's introduce a little notation for our events. I'm going to let capital G be the event that we drew a green ball, and I'm going to let these Roman numerals 1, 2, and 3 be the event that we chose from box 1, 2, or 3, respectively. Now, the probability that we choose a green ball, given we know what box we're in, is pretty easy because we're randomly selecting a ball from that box. Now, the first box has a total of 6 balls, and 2 of them are green. So if I were to go into the first box, the probability I would choose a green ball is 2 out of 6, or 1/3. The second box has a total of 6 balls, and 1 of them is green. So if we go into the second box, given we're in that box, the probability we draw a green ball is 1 out of 6. And finally, counting up the balls in the third box, where there are a total of 5 balls, 2 of which are green, given we draw from box 3, the probability we get a green is 2/5. But that's not what we wanted to find. We didn't want to find a conditional probability. We just wanted to find the probability that at the end of this experiment, we had a green ball. So I think it's going to be really convenient for us to condition on which box the ball came from and use the law of total probability. Now, in our experiment, we do have to go into one of the boxes, and we go into only one of the boxes. So that part of the experiment partitions the sample space. We will be drawing from one of these boxes, and there's no other option. And we cannot draw from 2 boxes at the same time. So I'm going to write the probability we get a green ball. I'm going to condition on which box we're in, and it's going to be the probability we get a green ball given we're in box 1 times the probability we're in box 1. Plus the probability we get a green ball given we're in box 2 times the probability we're in box 2. Plus the probability we get a green ball given we're in box 3 times the probability we're in box 3. Now, we just talked about these probabilities, this one, and this one. They were 1/3, 1/6, and 2/5. And the probability we chose from box 1, now these probabilities were determined by the fair 6-sided die that we rolled. And if we roll a 1, we choose from box 1. And that's going to happen with probability 1 out of 6 faces on the die. And if we got a 2 or a 3, we chose from box 2. And that's going to happen with probability 2 out of 6 faces on the die. And then the remaining things that we can roll, so a a 4, 5, or 6, those are 3 faces out of 6. So we have probability 3/6 or 1/2 of getting a 4, 5, or 6, and therefore choosing from box 3. So we know all of these probabilities. I'm going to put them together, and we get 14 out of 45. So that was an example of the law of total probability. We really didn't care about a conditional probability. We only cared about the probability we got a green ball, but bringing conditional probability in made things a little easier. Okay, so let's change up the experiment a little bit. I'm going to roll the fair 6-sided die. If we get a 1, choose from box 1. If we get a 2 or 3, choose from box 2. And if we get anything else on the die, I'm going to choose from box 3. Next, I'm going to go in and randomly select a ball from that box. And I don't want the probability that it's green. And I don't want the probability that it's green given it came from a certain box. I want to answer the question that if I went and performed this experiment and I showed you that I got a green ball, but you didn't see how the experiment went, I want to ask you the probability that it came from box 2. So before we wrote down as part of our probability of getting a green ball, the probability that it's green given it came out of box 1, 2, or 3. And in the case that it came out of box 2, there's 1 green ball out of a total of 6 balls. So the answer is 1/6 for the probability I get a green given it came out of box 2. But that's not what I'm looking for. I'm looking for the probability it came out of box 2 given that it was observed to be green. So again, I performed the whole experiment in a sneaky way over here, and then I said, aha, I have a green ball. What is the probability it came out of the second box? This seems backwards. If I knew it came out of the second box, the probability of drawing a green ball is easy to compute, but this is not. So it seems backwards, and that is where you want to use Bayes' rule, because Bayes' rule can help you turn around conditional probabilities and write them the other way. And in this case, those are much easier probabilities for us to compute. Okay, again, Bayes' rule is for times when your conditional probabilities seem backwards, when the other directions are easier to compute. And as I told you at the beginning of this video, we don't need Bayes' rule. We need Bayes for so many other things in statistics, but this one I think we can handle. So I want the probability that we drew from box 2 given that we observed a green ball. By definition of this conditional probability, this is the probability we got a green ball and chose from box 2 over the probability we got a green ball. So now I'm going to use conditional probability again to unravel that intersection probability. We talked last time about how we can unravel the definition of conditional probability. So I can write the probability of green intersect box 2 as the probability we came from box 2, given that we had a green ball, times the probability of a green ball. But that's not useful because that involves the thing we're trying to compute. And the other way I can write this intersection probability is the probability we got a green ball, given we drew from box 2, times the probability we drew from box 2. Now in this problem, we already know the probability of having a green ball. We've already computed that. But if we didn't, we would then condition on which box the green ball came from in order to expand this denominator. And now that we're down here, we know each and every one of these numbers. The probability of getting a green ball, given it came out of box 1, is 2 out of 6. Because there's 2 green balls out of 6, and I won't bring you through each and every number here, but the probability, for example, that we drew from box 1 is 1/6. So you can see the probability of getting a green ball down here again. Probability of getting a green ball, given we chose out of box 1, times the probability we chose out of box 1, plus the same thing for box 2, plus the same thing for box 3. And our numerator is the probability we choose a green ball, given we came out of box 2, and that is 1 out of 6. And the probability we chose box 2 is 2 out of 6 because we chose it when we got either a 2 or a 3 on our fair roll of a 6-sided die. So we turned a probability, a conditional probability that seemed backwards, into the other directions, the more natural direction for computing these conditional probability And in the end, we get 5 out of 28. Okay, so we can easily generalize Bayes' rule. What I want to do is take a sample space, which is the collection of all possible outcomes of an experiment, and we usually denote that by an omega. And I want to take some kind of partition of that space, which is some sets where we break the total space into a sequence of disjoint sets that if we union them together, we get the whole space back. I'm going to call those sets B1, B2, B3 out through Bn in general. Now, n was 3 in our previous example because these events, B1, B2, and B3, corresponded to choosing from box 1, 2, or 3. I'm going to let A be any other event, and in our ball and box example, that would have been the event that we choose a green ball. And now I want to know the probability that the event B sub j happened, given I know that the event A happened. Now, this is not a ball and box example, so maybe this is something that we can just write down directly looking at the problem. Maybe this is easy. But if it seems backwards, if it seems like the other direction would be easier, then we can use Bayes' rule. So I would write this as the probability of B sub j intersect A over the probability of A. And then I would unravel that intersecting probability in the numerator to be the probability of A intersect BJ times the probability of BJ. There's two ways to unravel it, but one way is just going to get us back to where we started and is not going to help. And then if you know the probability that A happens, that's your denominator. But if not, if it's easier to condition on which event B1 through Bn happened, then you can use the law of total probability to get this in the denominator. So this is the general looking version of Bayes' rule. Now, in the next video, we're not quite at Markov chains or Markov processes, but we are very close. And even if all of this stuff we've done so far is familiar to you, I think there might actually be something to learn in video 3. And that's where we're going to translate the law of total probability and Bayes' rule and some other rules of probability to a random variable setting. So we're going to get away from the idea of events happening and instead talk about the probability that a random variable takes on a certain value given conditional on another random variable taking on another value. So that's going to be in the next video, and I hope to see you there.